Okay, hello everyone. This is lecture 19. It's about the ellipsoid algorithm. So we've seen a couple of lectures on linear programming and referred to the fact that it is solvable in polynomial time, and the algorithm that can solve it in polynomial time is this ellipsoid algorithm. So what we're going to do today is a couple of things. First, I'm going to tell you about the ellipsoid algorithm for solving linear programs in polynomial time. And we'll see that, in fact, not only does it solve polynomial linear programs in polynomial time like expected, but it can even solve linear programs when they're not fully given explicitly. They merely have a separation oracle. I guess that might not make sense right now, but I'll explain what it means later in the lecture. And then we're going to see how to use this technique to solve a generalization of linear programs called semidefinite programs, which you may or may not have heard of. And the motivation for this will be from the max cut problem and trying to get a good linear programming relaxation for it. Okay, so let's get started. I would like to start to tell you about the ellipsoid algorithm. So recall that we saw 2 lectures ago that the general problem of linear programming, maximizing or minimizing a linear function in a bunch of variables subject to a bunch of inequalities, linear inequalities, it reduces in polynomial time to a much simpler problem, just the problem of testing whether a bunch of linear inequalities has a solution or not. It's called the emptiness testing problem. Together with the additional assumption that you can freely assume that the inequalities can include what I call like big box constraints. So all the variables are constrained, x1 through xn are constrained to be between some like minus r and plus r, where r is a really large number. It can have polynomially many bits in it, where I refer to polynomial in the bit representation of all the other constraints. So just to say it a bit more formally, the problem is you're given as input k, a polytope, which is the intersection of some linear inequalities like these ones, together with these big box constraints, as I mentioned, that each variable is bounded between some minus r and r. And you want to decide whether or not there's a solution for this, whether or not k is empty or not. Okay, so what I want to do now before I get into the ellipsoid algorithm is to claim that you can make this problem even a little bit easier on yourself. You can reduce solving this problem to resolving a quote-unquote robust version of this problem. And what do I mean by a robust version? Well, in the robust version, the input also is going to include a small number r, which you should think of as like exponentially small, but positive, so it can be written with polynomially many digits. And you're promised that either k is empty, or not just that k is not empty, but that k actually contains a tiny little full dimensional cube in it of side length r. So it's sort of robustly non-empty. So this is the problem that the ellipsoid algorithm can solve, this robust version, where k is either empty or it contains at least some little cube. And before we get to how the ellipsoid algorithm does this, I want to show you one more reduction, which illustrates that you can reduce to this problem also in polynomial time. And since in 2 lectures ago, when we were really talking about all the nitty-gritty details about polynomial number of bits, this and that, I'm only going to give you a proof sketch of this point to explain why we can reduce this robust version. So the first step of the sketch is to convert the input polytope k to equational form. So if you recall, this is the form. You can always reduce an LP to an equivalent form like this, where your constraints are that all the variables should be non-negative and that they should satisfy some equations. So there are 2 pictures here. So first, in Rn, you look at the positive orthant, all the points x that have all of their coordinates non-negative. And this ax equals b is going to define some subspace, like a hyperplane. And the case that k is empty is the case that this hyperplane misses the positive orthant. And on the other hand, the case that k is non-empty is the case that the hyperplane hits the positive orthant. And typically it could hit the positive orthant, in like a big range of points. But the picture I've drawn here kind of illustrates like maybe the trickiest, hardest case, when the hyperplane just barely hits the corner, for example, of the positive non-negative orthant. Okay, and so the linear programming problem, you have to decide, for example, given k like this, whether you're in the empty case or the non-empty case. And this non-empty case is sort of like not a robust case. This here, in this little picture, the set of points in K does not contain a full dimensional cube of some little size, but maybe it's just a point, maybe it's just the origin. So this is the problem you have to be able to solve. And what I want to show in this claim is that you can, again, like sort of rejigger the input such that the two cases, instead of being empty and non-empty, are like empty and like robustly non-empty, containing a little cube. So what's the idea behind this? Well, the point is that these, so if you have a hyperplane like this, ax equals b, and it misses the non-negative orthant, then what I claim, and this is kind of like these claims I was talking about before with the fact that the Gaussian elimination is in polynomial time and so on and so forth, is that these distances, sort of the distance by which it misses the non-negative orthant, cannot be like arbitrarily small. It can only be exponentially small, whereby exponentially I mean in the number of bits needed to write down, ax equals b. So if the input is ax equals b in your polytope k, these distances, if they're non-zero, if they're positive, then they have to be at least some like exponentially small amount. Okay, so this is why it's a sketch. I'm just saying take my word for that. And what this means is the following. Given that you know that, what you can do to kind of convert to a robust version of the problem is to change k to some k prime, where you take all of these equality constraints, ax equals b, and you relax them a little bit to two-sided inequalities, where you allow a teeny bit of slack, plus or minus some exponentially small r prime. Okay, so you actually change these equalities to slight, two-sided inequalities, like b plus or minus r prime in every coordinate. And what effect does this have on the picture, this little move? Well, on one hand, it sort of takes the feasible region from just this hyperplane intersect the non-negative orthant to sort of this very thin slab intersect the non-negative orthant. But if you make this r prime like small enough, the empty case will still be empty, okay, because you've made this r prime small enough so that even thickening this hyperplane a little bit won't hit the non-negative orthant. But on the other hand, when you do this thickening over here, you'll actually contain a whole like full dimensional, polytope now. If even you were in the worst case before, where the hyperplane just barely touched the non-negative orthant, in particular, you'll contain this little cube here. Okay, so if you just take this k, which you don't know anything about, you don't know whether you're in the empty case or not, and you thicken these equations to like slight slack two-sided inequalities, then it preserves whether you're in the empty case or the non-empty case. But furthermore, in the non-empty case, it gives you the property that the polytope contains at least a teeny tiny full dimensional cube. Okay, so that's sort of the end of this sketch. So if any questions about that, let me know. Okay. So now we've reduced the problem that the ellipsoid algorithm truly solves, which is the robust emptiness testing problem. So let me give it to you in full details here. So given for the ellipsoid algorithm is the following things. The input is a bunch of inequalities defining a polytope k. Think of this as just like the ax equals b kinds of inequalities. And also given as input to the ellipsoid algorithm are two numbers like big R and little r. And you should think of R as being, exponentially large in the number of bits needed to write k, and little r as being exponentially small. But in any case, they're just these two inputs, capital R and little r. And you're given a promise. The promise that you're given in the ellipsoid algorithm is that you're in one of two cases. Either k is the empty set, there are no solutions to the inequalities defining k, or you're promised that not only does k have at least some points in it, it contains a full dimensional cube of side length little r, and it's contained in the full dimensional cube of side length r centered at the origin. Okay, so let me draw a picture. Like the algorithm sort of, well, the picture is like this. So the algorithm gets this parameter capital R, and it knows that should R exist, should k exist, should k be non-empty, then it's somewhere contained in this cube centered at the origin of side length capital R or capital 2R, whatever. And K may be empty, but it also knows if K is not empty, then I see there's a question, 1 second. If K is not empty, then the algorithm is promised that K is, it contains like a little cube of side length little r. Now it doesn't know where this little cube is. It just knows wherever K is, it has at least some full dimensional little cube of side r in it. Okay, and the goal of the algorithm is just to tell which of the two cases it's in, whether we're in K is truly empty, there are no solutions to K, or whether K is non-empty. But in an effort to try to decide this, it gets to rely on these two assumptions about capital R and little r. So there's a question in the chat about what's the difference between little r and capital R. Maybe the description I gave subsequently will clear it up. So little r and big R are parameters known to the algorithm. Big R is the side length of a big box that's like known to the algorithm that's guaranteed to contain K should it exist. And little r is like sort of like a robustness parameter, like the algorithm's promise that like K at least contains a little box of side length little r. Okay, and the running time of the algorithm should be polynomial in the input size of K, the number of bits it needs to write down all the inequalities. But it should also run in time polynomial in the logarithm of capital R and the logarithm of 1 over little r. Or to put it another way, it should run in time polynomial in the number of bits needed to write down big R and the number of bits needed to write down little r. Okay, and this was important for solving LPs, as we saw, because in general, the big box constraints, capital R, that you can assume exist without loss of generality, involve taking R to be like exponentially large in the number of bits of K. And similarly, the little r that we talked about in the previous few slides, that you can assume sort of exists without loss of generality, is also going to be exponentially small in the number of bits that are used to write down K. Okay, any questions about this? Oh, there's a question that says, could you repeat exactly what angle brackets K means? That's a great question. I forgot this. This is notation from like 2 lectures ago, so it's no wonder that's hard to remember. For these lectures, I'm writing like angle brackets around a mathematical object to denote like the number of bits needed to write it down. So like if K is just a number, angle brackets is basically the logarithm of that number. It's like the number of binary digits you need to write it down. If K is a fraction, then it's the number of bits needed to write the numerator plus the number of bits needed to write the denominator. If K is a vector, then it's like the sum of the encoding lengths for all the numbers in the vector. And in this case, K, where K is basically like a matrix together with a vector, it's like the number of bits needed to write down all the numbers in K. There's another question that asks, to convert K to a robust version, should we have log 1 over little r to be at least the number of bits of K? Yeah, exactly right. So let me go back a couple of slides. I showed you here this sort of little, the reason why we can sort of assume without loss of generality this little r, or r prime as I call it here, exists. And as I mentioned back on this slide, this little r, you have to take it sort of quite small. It has to be like 2 to the minus polynomial in the number of bits of K. Okay, and so logarithm of 1 over little r is like polynomial in the number of bits of K. So in order for everything to be like a polynomial time algorithm, just given K, where polynomial means in the number of bits you need to write K, you have to set these capital R's and little r's to be like exponentially large, or in other words, they have to be written with a number of bits that's polynomial in the number of bits needed to write K. Okay, these are good questions, so keep them coming in the chat. Right, so to summarize, this is the problem we have to solve. It's sort of like hunting for K. You're going to like hunt for K, and it starts inside this big box, capital R, and you're going to try to see if you can find a point in K. And you have this like guarantee that like you don't sort of have to hunt indefinitely. Like K could not be like infinitesimally small. Like if it's going to exist, it has to be at least at least the size of this small cube of side length r. And you're quite restrictive. You have to run in time polynomial in log of these big R and 1 over little r. Okay, great. So I said here that the task is to decide between the two cases, either that the inequalities defining K make K non-empty, or they're unsatisfiable, there's nothing in them. But actually, I want to tell you that it's sufficient to do something slightly different. When you're designing this algorithm, the ellipsoid algorithm, in fact, it's sufficient to like assume, to like work under the hypothesis that k is non-empty and try to find a point x and k in the allotted amount of time, polynomial in the number of bits needed to write k, log of big R, and log of 1 over little r. And what's the reason for this? Well, suppose you had an algorithm that could do this, that like under the assumption that k really existed, it could always find in the appropriate amount of time a point x in k. Well, you could also use that to solve the decision problem, the problem of deciding if k, is empty or non-empty, because you could just run this argument that tries to find a point in k. If k is non-empty, then this algorithm will succeed by your assumption. And if k is empty, this goal doesn't really say what happens if you run the algorithm. But if k is empty, like this algorithm is not going to find any point in k because there is no point in k if k is empty. And so, the algorithm will just fail to find a point of k, and then like the meta algorithm can say, okay, like it must be that k equals empty. Okay, so that's sort of how you reduce the empty versus non-empty decision problem to the task of finding a point, assuming that set is non-empty. And now we're sort of finally set up. So like now you can really start to get ready for the algorithm. Once again, like you're given these inequalities defining k, defining this polytope. You're promised that k is inside this giant box of side length r, centered at the origin. You're also promised that k at least contains like a tiny box of side length little r, and you just have to find a point in k. And of course, you can like, you're given k, so you can look at the inequalities that define it. And so one thing you can do easily is test whether a given point is in k or not. If you have a potential point inside this box in mind, this big box in mind, x and Rn, like literally numbers, you can easily see if it's in k or not, because you can just plug it into the inequalities defining k and see if they're all satisfied. So this is one thing that you can certainly do, and that's going to get us started in this ellipsoid algorithm. So true to its name, the ellipsoid algorithm involves ellipsoids. This is a little bit just because they're convenient. So initially, we assume that we're promised k is inside a big box, but the first thing we're going to do is like weaken that assumption in our minds and just pick the sphere or ball of radius, well, the ball that contains this big box of radius of side length capital R. So the ellipsoid algorithm is iterative, and the way it works is it always maintains some ellipsoid, like a stretched sphere, some ellipsoid Q, which is guaranteed to contain k. So remember, we're in the assumption here that k really does exist and is non-empty. And since you're promised that k is inside this big box, you're just like, well, I want to work with ellipsoids. Let me just put like an even bigger sphere Q around this box. And that'll like, give me my initial satisfaction of the invariant that I have this ellipsoid Q that contains k. Okay, so the very first thing that happens in the algorithm is you've got this Q in your hands, and you just check whether the center of Q is in k. Okay, so the center of Q at the beginning is the origin, and you just plug all zeros into k and see if it satisfies all the inequalities. And if it does, then great, you found your point in k, and the algorithm is done. But usually that doesn't happen. So what do you do if the center of Q is not in k? Well, here's the thing. If the center of Q is not in k, it means when you plugged in the center of Q as numbers into the inequalities defining k, at least one inequality was not satisfied. And that sort of violated inequality or violated constraint is called a separating hyperplane. Why? Well, the picture is this. So you have this hyperplane, which is, defines one of the facets of k. And in this picture, this orange one is a separating hyperplane because it has all of k on one side, sort of the right-hand side on your screen. And but the origin is on the left side, or is sort of outside it. So this orange thing is like a half space, and it's one of the half spaces or inequalities defining k. And it's separating in the sense that like k is all entirely contained inside it, but the point that you tested is outside it. Okay, that's what the meaning of separating hyperplane is. Good. So the algorithm can certainly find that. It plugs the center into the inequations defining K and picks out one that's not satisfied. That's what happens if the center is not in K. And so now what does the algorithm know? Let's see if I can annotate this in PowerPoint. So what does the algorithm know? It kind of knows, this is terribly funny annotation, but it knows that K, wherever it is, has to be in this sort of dome, the intersection of this half space with the ellipsoid that it's currently holding on to. Right. So the next thing it does is it just sets it gets a smaller ellipsoid containing K. It sets Q prime to be the smallest ellipsoid that contains this dome. So that contains the intersection of Q with this separating half space, which might look like this in the picture. This is the Q prime. This is the smallest ellipsoid that contains this sort of dome here. Okay. And let me just assure you, it's like a pretty simple matter of linear algebra. If you like know the ellipsoid Q and you know this half space that like cuts off a piece of it, it's a pretty simple matter of linear algebra and geometry to figure out Q prime, the smallest ellipsoid that contains this dome. And then you iterate. So actually, let me just go back here and say what I mean by iterate. So now you're hanging onto this, blue Q prime, and you do the same thing. You know its center, so maybe its center is perhaps right here, perhaps right here. Maybe it just misses K. And so you check whether the center is in K. If it is, then great, you found a point in K. Otherwise, when you plugged it into the equations defining K, there's at least one inequality, perhaps this one, where K is all on one side of the inequality, but the point you tested here, the center was outside. So then again, you know that K, wherever it should be, is inside this region, the intersection of your current Q prime, is a great drawing, and your half space. Okay, and then you pick the smallest ellipsoid that contains this new region, which I don't know what it looks like. Maybe, okay, that's a terrible ellipsoid. Okay, I can't draw with a mouse, but some ellipsoid that looks like this, that contains the dome that you just cut off, and you iterate. Okay, so let me tell you about the analysis. The analysis is, there's a very easy lemma, which I won't prove, but like really it's easy when you write down a little bit of analysis about this Q prime. That says that the volume of Q prime will always be a little bit smaller than the volume of Q. It'll be smaller by at least a 1 minus 1 over 3n factor, where n is the dimension. It's not hard to prove. And that's great, because it means if you repeat this algorithm order n times, then the volume will go down by like 1 minus 1 over 3n to the power of n. And that's like x of minus 1 over 3n to the power of n. That's like a constant. So repeating it like a constant times n number of times, the volume goes down by a constant factor. So you're really making a lot of progress. And you can do this even more times to now like start driving the volume down geometrically. So now it's a pretty easy calculation as well. Again, this is like a proof sketch, but the volume of the initial sphere, Q initial, it's like, a sphere that's like in n dimensions, and like it's got this radius that's like capital R. So it's at most, you can check like R to the n times n to the n. And you know that K contains this little cube of side length little r, which has volume little r to the n. And therefore, like, as soon as the ellipsoid you're hanging onto has volume smaller than little r to the n, like the algorithm has to stop, because like it, you can't have like an ellipsoid that the ellipsoid always fully contains K. So like its volume cannot get lower than little r to the n without you finding a point in K. There's a question about whether K has to be convex. I'll get back to this question in just a second. And therefore, you will find a point in K after how many rounds of this? Well, you have to drive this initial volume down to this volume, and like it halves every order n rounds. And so the number of additional rounds is like logarithm of this, which is good. This is going to give you the log r term. You'll collect up some extra poly n terms, which are fine. And you'll also get the log 1 over little r. Okay, and this is what we were shooting for, poly n times log of capital R over little r steps. Okay, so in the actual details of the algorithm, there's like a little bit more pain because you have to do actually like the numerical arithmetic algorithms to keep track of q prime and so forth, but that's very boring, and this is just the idea of the algorithm. The question from one student was, does K have to be convex? It's a good question. This algorithm kind of looks like you could be hunting for any shape. The critical aspect of it being convex, K, that's a wonderful picture, a version that's not so crazy, yeah, is the existence of this separating hyperplane. So for this volume to go down, you really need to be like chopping by hyperplanes. You need this property that like whenever you draw a hyperplane through the center of an ellipse, and then take the smallest ellipse that contains that chopped off part, the volume goes down a little bit. And yeah, so you need this shape to be convex because you need that whenever you test a point and it's outside the shape K, there should be a hyperplane that separates K from the point. And so if K had some like weird non-convex parts like, this, then you would have a point like the center here, which is outside K, but there's no like hyperplane which separates the point from K. So hopefully that answers that question. Okay, we have another question. In the claim, the question is about, in the claim that the volume of the initial sphere, Q init, being at most r to the n times n to the n, where does the n to the n come from? Oh, this is because you need to know, like, if I ask you, like, what is the volume of a sphere of radius 1 in n dimensions, there's a formula for that, and it's something like n to the, it's n to the order n. So I didn't make that point, but that's the case. Yeah, I forget the formula off the top of my head, but it's like in n dimensions, the volume of a unit sphere is like n to the n, and then the capital R to the n is because it's like a radius r sphere. Okay, great. So now let's get actually back to this point about whether or not K needs to be convex, because it does need to be convex, but a related thing is a crucial observation. And this crucial observation is that the algorithm doesn't really need to know K per se. It doesn't really need to have the inequalities defining K like written down in front of its face necessarily. How did the algorithm really interact with K? Well, it needed to know capital R and little r, and it needed what's called a separation oracle. What's a separation oracle? Separation oracle is a way where you like some kind of like black box that gives you information about capital K. And a separation oracle, I'm defining it here, it takes in a point z in our n dimensions, and it outputs one of two things. It either outputs like just the correct statement, hey, this z is in K, or, and that's like when you test whether or not the center is in K, you want to know this question, or when z is not in K, the separation oracle gives you back a separating hyperplane explicitly. It says, nope, not only is z not in K, but like here's an inequality that z does not satisfy, despite the fact that all points in K satisfy, despite the fact that this half space contains K. So this is the definition of a separation oracle, and it's really the only thing the ellipsoid algorithm needed in order to do its algorithm, to interact with K. And this is actually a really useful fact for algorithms. Yeah, this just note also points out this inequation does not have to be a facet of K. The way we were showing it, it was always like an inequality defining a facet of K, but it doesn't have to be. Just any separating hyperplane. And the reason that this fact is so cool is because it means, in certain sense, you can actually solve linear programs with exponentially many constraints, or in fact, even more than exponentially many constraints. as long as you can efficiently implement a separation oracle. So we won't get into this too much, but this idea has a lot of applications in algorithms. And the idea is like an algorithm can maybe like imagine an LP that it wants to solve that has n variables. That's maybe like, you know, polynomial, but it has maybe exponential and m many constraints. And so the algorithm cannot explicitly write the LP it wants to solve down. But as long as it can solve this task of like given a point, testing whether it's in the LP, and if it's not, finding a separating hyperplane, then you can use the ellipsoid algorithm to solve the linear program. And this is exactly what's needed for this new kind of algorithm called semidefinite programming, or this new kind of optimization problem, which is a generalization of linear programming called semidefinite programming. And that's what I'm going to get into next. Any questions right now? Yeah, there's a question. It says, does the same argument work with the rectangular boxes instead of ellipsoids? Maybe allow rotations. Great question. It does not work with boxes or even rotated boxes. I guess it's unfortunately a problem that like if you take a box and, I guess it must be that if you take a box, I don't know off the top of my head, but if you take a box, oh, well, I guess the problem is if you take a box and you cut it with a hyperplane, what you're left with is some kind of pyramid-y thing, a simplex. And if you now wrap that back up with the box, unfortunately, I guess it's the case that this new box need not be noticeably smaller than the original box. Maybe you won't have this property, that volume decrease that you had with ellipsoids. That said, there's a chance I'm wrong because I know there is, somebody, shortly after the ellipsoid algorithm came out, they were like, oh, it's quite annoying to work with ellipsoids. Can you work with simplexes, like these, pyramids? And there is like a version of it that works with simplexes, and it works. And you're always maintaining the simplex that contains the convex set. But apparently it's like actually more annoying to analyze than the ellipsoid argument. But it is true that these ellipsoids are not like super critical, and like you can do it with like simplex shapes instead. Okay, good. So let's go on and start to talk about semidefinite programming, which, as I mentioned, is a kind of generalization of linear programming, which is very useful for algorithms, especially for constraint satisfaction problems and other optimization problems. And to motivate this semidefinite programming, we're going to think about a very simple optimization problem, the max cut problem, which we've mentioned before already in this course. So the max cut problem is quite simple. In the max cut problem, you're given a graph, G, an undirected graph. And unlike min cut, you're trying to do the opposite. So you're trying to find a subset of vertices S, like these ones circled in yellow, so that S as a cut cuts as many edges as possible. So remember that an edge is said to be cut if it has one endpoint in the set S and one endpoint outside the set S. So in this particular example, almost all the edges are cut. This edge is cut. It goes from inside to outside. This edge is cut. This edge is cut. This edge is cut. And despite the picture, this last edge is not cut because its endpoints are both in S. Okay, so this cut 4 edges, and that's actually the maximum cut in this graph. It's impossible to partition the pentagon into 2 sets such that it cuts all the edges because the pentagon is not a bipartite graph. Okay, so max cut is given the graph, find the cut of largest cut size. And as you know, this is an NP-hard problem. And in particular, that means, unlike the min-cut problem, which we saw last time can be exactly solved efficiently using a linear programming relaxation, you kind of know that's not going to happen for max cut, because otherwise you'd be solving an NP-hard problem in polynomial time. Okay, so what that means is, if you try to do this paradigm of like writing down an integer linear program that captures maximum cut, relaxing it to a linear program, and hoping that's not such a bad relaxation, maybe solving this linear program, getting an optimal sort of fractional solution, and then rounding it to a true solution S, this paradigm we talked about last time, well, you're not going to get the situation that this always gives you the optimal maximum cut, because then, max cut would be in polynomial time. And in fact, this paradigm fails really badly for maximum cut. So it's a great strategy in general facing an optimization problem. Formulate an ILP, relax it to a linear program, but for max cut, doesn't work well at all. And if you try it, the only thing you'll really be able to prove about this strategy is that the size of the cut it achieves, whatever however your strategy works, the size of the cut it achieves, the number of edges from S to S complement, will be at least a 1/2 fraction of the optimum. Which is okay, but we saw like a variety, there are a variety of really simple algorithms that can achieve the same approximation behavior. So you don't really need linear programming to get this kind of weak result. In fact, in the de-randomization lecture, we talked about how you could just pick a random partition and it would cut half of the edges, half of all the edges, which is certainly half at least the optimum max cut in polynomial time. And this was easily de-randomizable. Okay, so that's a shame that this powerful linear programming technique does not work, but it's going to be the reason we extend this version called semidefinite programming. And as a bit of a spoiler, using this tool of semidefinite programming, we'll actually be able to get a polynomial time algorithm that achieves a much better so-called approximation factor. It'll give you a polynomial time algorithm that returns a set S that always achieves at least 87% or 87.8% of the maximum cut, which is pretty great. And in fact, it's known that there's evidence that doing better than this 87.8% cannot be done in polynomial time. It's unique games hard, and we'll say what this means in a much later lecture of the course. Okay, so this is to psych you up for trying to develop a generalization of linear programming that will help us solve max cut. Okay, so even though I told you it's gonna fail, let's talk about this standard paradigm for max cut of trying to write down an integer linear program that exactly captures it and relaxing it to a linear program. Okay, so in an integer linear program, we usually introduce variables. We're going to introduce variables xv, one for each vertex, with the intent, they're supposed to be 0 or 1, and the intent is that xv should be 1 if vertex v is going to be in the set S, and 0 otherwise. Okay, so xv in the integer linear program is supposed to be the indicator set for a set S. But now we need to start talking about whether or not S cuts or doesn't cut various edges. And so after a few moments, or in fact inspired by the min cut LP we talked about in the last lecture, you would be motivated to introduce variables y, so VW, for every pair of vertices VW that are supposed to be 0 or 1. And again, with the intent that y VW should be 1 when x, when thought of as a cut, actually cuts the edge VW. Or in other words, YVW should be 1 if and only if XV differs from XW. So that's going to be tricky to enforce with linear constraints, but let's just go on for now. What is the objective? Well, we're trying to maximize the number of cut edges. So if we could set all these variables up like so, the objective function would be to maximize the sum over all edges VW in the graph of YVW. That would exactly just count the number of edges cut by the set indicated by S. And that's a perfectly linear function. It's just the sum of some of the variables. Okay, but what we have to worry about is this constraint that we're trying to capture. I mean, of course we have to worry about the fact that this is an integer linear program, and like we cannot eventually insist that xv and yvw are just 0 or 1. But like this is the standard worry that we've always talked about in this paradigm. We're of course going to relax these constraints to make an LP, or we're going to try, where we're going to let xv be a real number between 0 and 1, and yvw be a real number between 0 and 1. But even if we do this, we have this difficulty that it's not clear how you can enforce this constraint with linear inequalities. And it's quite funny, actually. If you think back to min cuts, I know we didn't talk about it too much, but at the very end of last lecture, we did see a linear program that was capturing min cuts. And in that linear program, you see, one way to try to express it is to say that yvw should be at least the absolute value of xv minus xw. Okay, and think about these variables as taking 0, 1 values. This sort of exactly works. You know, as long as xv and xw are different, this right-hand side is 1, and so you're obligated to make yvw 1. But if they're the same, you're allowed to make yvw 0. And for min cut, you would, of course, always be trying to make these y's as small as you're allowed. Now, this, at first, does not look like a valid linear inequality for linear programs because it has these absolute value signs. But actually, it's fine because if you think about it, this inequation can be converted to two proper inequalities that capture it. You know, you have to just say that yvw is at least xv minus xw, and yvw is at least the negative of xv minus xw. So this is just shorthand for two inequalities that you really could include. Well, on the other hand, for max cut, you might, so in max cut, you're always trying to make the y's as big as you can. And you could enforce this if you could write down that like yvw is at most absolute value, because then again, that would say that if xv and xw get different 0, 1 values, you're allowed to set yvw to be 1. But on the other hand, if xv and xw are the same, then you're obligated to set yvw to be 0. But unfortunately, like this two-sided, this inequality, you just can't write it as like this. You can't convert it to two like normal inequalities, right? If you just think about it, you know, this doesn't work. So that's the difficulty. So we're a little bit stumped at this point. Even if we're willing to go to an integer linear program, we're a little bit stumped as to how we can encapsulate this constraint. Any questions? There's a question. The question is it known whether we can express yvw equals the indicator that xv not equal to xw through a set of linear constraints, say by defining a few more variables? Short answer is no. You might say like, oh yeah, maybe I'll try to play around. I'll try to add a few more variables, and I'll exactly encapsulate this. I guess basically the answer is no. But you can still have a smart idea. The question is there a result that proves this is impossible? I guess it's like saying if you allow yourself to have an integer linear program, can you encapsulate this with inequalities? I guess I would say provably no. I don't want to try to prove it on the spot, but I would say provably no. Probably not without exponentially many inequalities. That's my guess, but don't quote me on that. My guess is not without exponentially many inequalities. But okay, there is going to be a smart idea though, and this smart idea came from circa 1990 in some paper of two people, Delorme and Poljak. And let me try to tell you about their smart idea. First thing, this is not essential to them, but to explain their smart idea, we're going to make a notation change. It's kind of my favorite notation change. Instead of using 0 and 1 for the xv's, we're going to use plus or minus 1. Okay, so now switch in your mind xv to be like plus or minus 1. And now also switch in your mind yvw should also be plus or minus 1. And you should it should try to be the product of xv times xw. Okay. And so there, notice that means that like yvw is supposed to be plus 1 if xv and xw are the same, because plus 1 times plus 1 is 1, and minus 1 times minus 1 is 1. And yvw should be negative 1 when xv and xw are different plus or minus 1 values. So again, it's just changing notation. This is going to be like the constraint that it's very hard to encapsulate, but I wanted to switch notation like that. And with this switch notation, the objective function is still fine. With this switch notation, you see this little expression here, a half minus a half times yvw. Remember, this yvw is 1 if xv and xw are the same. So when you plug 1 in here, you get a half minus a half, which is 0. So this expression is 0 if xv is the same as xw. And if xv is different from xw, then yvw is minus 1. So this expression is 1. So with this new notation, this parentheses expression is the indicator that xv differs from xw, and so this objective function, which is still a linear objective in the variables yvw, exactly encapsulates max cut. Okay, so what I'm trying to say here is, I've just switched notation. So far, this program, if you could carry it out, exactly captures max cut. Okay. So let me throw in a few more equations that are fine. Certainly, if you have this set up, then yvw should equal ywv. So I can throw that in. That's a linear inequality, or a linear equality, so that's fine for LPs. And again, if yvw is supposed to equal xv/xw, and xv's are supposed to be plus or minus 1, then yvv should always equal 1. And that's another linear equality, so there's no trouble in throwing that into an LP. And let me just pause again to say that, like, now, this program also captures max cut exactly. Okay, I no longer have to explicitly say xv and xw are plus or minus 1 valued, because, well, if you have that yvw equals xv/xw, and you also know that yvv is 1, then it means xv squared is 1, which means xv is plus or minus 1. Okay, so still, this is not like a linear program or anything, but it still captures max cut exactly. And furthermore, this piece, without this tricky constraint, is a linear program. It's a linear objective, linear equalities, in fact. So that's good. Okay, so here's really the smart idea of the Lohrmann-Poljak. It's going to say, let's take this LP, kind of forget about this equation, but instead imagine that we put this LP together with this weird constraint. And the constraint is, given the y's, just that there should exist some real numbers xv such that yvw equals xv/xw. Okay, so this is a weird constraint. But let me call this, for reasons we'll eventually see, the moment constraint. And I still want to say that this linear program LP, together with this moment constraint, exactly captures max cut. This moment constraint is some weird constraint. It's not a linear inequality constraint, but we're still at the point where these two things together exactly characterize max cut. Okay. So now I can finally say their idea. And their idea is to try to enforce moment using linear constraints, just on the yvw's. So the only variables are yvw's. And this moment constraint says there exist real numbers like x such that yvw equals xv/xw for all v and w. And that's not a linear constraint, but like the idea is try to encapsulate it with some linear constraints. Now, we're not going to be able to succeed in doing this exactly, because if we could succeed in doing this exactly, then, well, the conjunction of everything would be a linear program, which we could solve in polynomial time, and then max cut this NP-hard problem would be in polynomial time. But just like with this sort of ILP to LP relaxation paradigm, we're going to kind of try to do a good job of encapsulating these moment constraints. So let me talk about this heuristically for a bit, and then I'll get talking about it properly later. Right. So this is the idea, to try to enforce these moment constraints using linear inequalities on the yvw's. Well, suppose we didn't try to enforce them at all, and we just took the LP constraints and we gave those to the ellipsoid algorithm. The ellipsoid algorithm can, solve linear programs. And I'm going to be a little bit slightly heuristic in the following discussion for a bit. We handed those the LP inequalities, actually they're equations, off to the ellipsoid algorithm without this moment constraint at all, and said, hey, ellipsoid, solve this for us. Okay, so ellipsoid would solve it. And maybe it would return some values like yvv. All the yvv's are 1. That's a constraint. It's got to satisfy that. And maybe all the other yvw's are like some tiny value. Actually, I think I meant to write here negative of 2 to the poly n, not 2 to the minus poly n. I meant to say some like super negative value. Remember, the objective is to, no, I should have written like, well, anyway, imagine it gave you back a bunch of like negative values for the y's. Well, it turns out that the giant negative values for the y's are not going to solve the or satisfy the moment constraints. And so imagine the ellipsoid did this to you. Ellipsoid algorithm did this to you, and then you came back and said, "Hey, just a moment, ellipsoid algorithm. I forgot to tell you one constraint in the k you should be solving," and it'll give back. Imagine you tell the ellipsoid algorithm, "I've actually got a separating hyperplane for you. It's the sum of all the y's should be greater than or equal to 0. I forgot to tell you that constraint, sorry." And it's actually legitimate for you, if you're trying to capture the moment's constraints, to say that this is a valid constraint. What I'm trying to say is any YVWs that satisfy the moment constraints must satisfy this inequality. And the proof of that is quite simple. You see, this sum of all the YVWs, if there really are x's, real numbers x's, that satisfy YVW equals XV then the sum of all the YVWs is equal to the sum over V and W of XV which by arithmetic is equal to the square of the sum of the XVs, and the square of a real number is non-negative. So this is sort of like a valid inequality for any solution y that satisfies the moment constraints. So you can, if the ellipsoid algorithm returns some y's that don't satisfy this inequality, you can just say, "Oh, sorry, ellipsoid algorithm, I forgot to mention you should also satisfy this constraint." Okay, and the ellipsoid algorithm will be like, "Oh, fine." So it'll like put that constraint in and like chop off like half of an ellipsoid, and like it'll keep going. Okay, we're using the fact here that the ellipsoid algorithm really only needs this separation oracle. And we're sort of trying to build a separation oracle for the set of all y's which satisfy this moment constraint. This is a bit tricky, so let me know if you have questions. Okay, so maybe you hand that off to the ellipsoid algorithm, and maybe now it comes back and it says, "Okay, I have a new solution for you. Y11 is 1 in my solution, and Y12 and Y21 are 100, and Y22 is 1, and dot, dot, dot." And you say, "Well, just a moment, ellipsoid algorithm. I forgot to tell you a constraint on the y's. I forgot to tell you this constraint, that Y11 minus Y12 minus Y21 plus Y22 should be non-negative." And that'll actually force the ellipsoid algorithm to go back and revise its solution, because 1 minus 100 minus 100 plus 1 is not non-negative. Okay, and again, this is valid for any y's that satisfy the moment constraints. And here's the proof. If you have y's that satisfy the moment constraints, then this y11 minus y12, et cetera, is equal to x1 minus x1 x2 minus et cetera. And again, by a little bit of arithmetic, this is exactly the square of x1 minus x2, which of course is non-negative. So y's that satisfy this moment constraint will also satisfy this linear inequality on the y's. I'm getting a question. The question is, could you re-explain the moment constraint? So the moment constraint is, it's some kind of constraint on a collection of variables called YVW. You have one variable for each pair of vertices in the original graph. And the constraint on these collection of y's is that there should exist a collection of real numbers called xv, one for each x sub little v, one for each little v vertex in the graph, such that YVW is equal to xv times xw. Okay, so not all collections of y's are such that you can find x's that satisfy this. But some collection of y's have this property. It's kind of just hard to characterize them, but and I'll explain this a bit more later, but what we're trying to do is find some linear inequalities which are true of all collections of variables y which satisfy this property. It's pretty tricky, but that's what's going on. Okay, so maybe now you tell the ellipsoid algorithm, "Oh, I had this separating hyperplane, so go back and find me a new solution. So ellipsoid will be like, all right, and it'll chop its ellipsoid with this half space, get a smaller ellipsoid, keep going. And maybe now it'll give you the same thing, but with y1, 2, and y21 being negative 100. But then we're going to say, oh, I forgot to tell you, ellipsoid algorithm, here's another constraint that the y's, I forgot to tell you, are supposed to satisfy. And notice this new solution doesn't satisfy this new constraint. And it's a valid constraint again, in the sense that any y's satisfying moment satisfy this inequality because of, well, you can change these minuses to pluses. There's another question. I guess this moment constraint is quite confusing. The question is, are we quantifying twice over little v in the moment constraint? I don't think so. I don't think I've written anything wrongly. This means like, the moment constraint is that there exists a vector of x's, one real number for each vertex in the graph, such that for all pairs of vertices in the graph VW, YVW equals the product of XV and XW. Okay, so as a side note, I just explained to you why any y's that satisfy this very, I guess, hard to understand condition, it is a hard to understand condition, why y's that satisfy this hard to understand condition at least must satisfy these two inequalities. Also the inequality that their sum of all the y's is non-negative. That was the first one. And notice actually that this inequality here, since we also know that one of our constraints is that y12 equals y21, and another one of our constraints is that like y11 equals 1 and y22 equals 1, these imply that 2 minus 2 y12 is non-negative. Similarly here, and together these imply that y12 is at most 1 and at least minus 1. Okay, and that's nice. So I'm just observing here that, the equalities we have, that yvw equals ywv, that we can put into the linear program, and the equality that yvv equals 1, that we can put into the linear program, plus these inequalities, which are consequences of the moment inequality, enforce that all the variables y are between minus 1 and 1, which is a reasonable thing. That's something that should be true. Okay, but what's going on here? I mean, this is definitely a tricky thing I've been telling you about. So let me try to explain what's happening, or what I was doing with these examples where I was imagining running the ellipsoid algorithm and sort of implementing a separation oracle where I kept telling the ellipsoid algorithm, oh, I forgot to mention this inequality, and I forgot to mention this inequality, and so forth and so on. So one thing that was always happening is we would take some constants, some real constants, CV, and we would observe that for any real values x, if you sum up CV xv and square it, it's non-negative. That's a fact of life. Let me just expand that out. Oops, there's some sort of weird PowerPoint bug here. This should say C sub v, not v super c. Let me try to draw that here. Scribble this out. Okay, so if I expand this out, it means like just this is a fact of life about real numbers for any green c's. And therefore, if y's are numbers which satisfy the moment constraint, if y's are such that you can find reals x and x, xv, one for every vertex, such that this equation holds, then this constraint will also be satisfied by the y's. Okay, to repeat, any y's that satisfy the moment constraints must satisfy this green box constraint for every choice of real vectors C. And notice that these are linear inequalities in the y variables. So what I'm saying is any y's that satisfy the moment constraints must satisfy infinitely many different linear inequalities, all the ones that look like this, for some choice of real numbers C sub little b, one for each vertex. And this, what's called the SDP constraint, or what I'll call the SDP constraint, is to imagine adding all of these linear inequalities for all vectors of real numbers C. Now, this is actually infinitely many inequalities that we're going to imagine including into a linear program. But remember, I told you, like, you know, the ellipsoid algorithm is so great, it can solve LPs even if you have like exponentially many or even infinitely many inequalities, as long as you can do this separation oracle. So I'll talk about this in more detail, but that's where this is going. So this SDP constraint is actually infinitely many constraints on the y's, linear inequality constraints, one for every choice of real vectors C, which are satisfied by any y's that satisfy the moment inequality, moment constraint. So this is what we're going to imagine doing. If you recall, we set up some kind of system that exactly captured max cut. It was some linear program involving these variables y. And it exactly captured it if you threw in these moment inequalities. In fact, let me go all the way back to that and just remind you of that. It's right here. So this is the LP, this part that's circled in white. It just involves the variables y. And we argued that if you could sort of solve this while enforcing this thing, which is the moment inequality, moment constraint, then you see, first of all, this fact, together with the moment constraint, would imply that these xv's have to all be plus or minus 1. And then, you know, yvw will just be plus or minus 1, depending on whether xv and xw are the same or not. So xv, the x values now can be thought of as like a cut. Let's say all the plus 1 vertices are in the set S, and all the minus 1s are in the complement. Yvw is plus 1 if the edge vw is not cut, and it's minus 1 if it is cut. And then this expression is 1 if the set defined by x cuts the edge vw, and it's 0 otherwise. And so this sum represents the number of edges cut by the set indicated by x. So just as a reminder, this LP, together with this moment constraint, exactly captures max cuts. And what we found is that like this moment constraint implied like infinitely many inequalities, but linearly inequalities. And somehow we're going to try to add all these infinitely many inequalities to this LP and be like, oh, I have an LP now with like, you know, n squared variables and infinitely many inequalities, but I'm going to just try to solve it anyway. And hopefully this will do a good job of capturing the true thing that we were trying to encapsulate, this weird moment constraint. Okay. So let me go back to where we were. Okay, so again, we're going to try to enforce this moment constraint, which if we could exactly capture it, would give us max cut exactly captured, with this SDP constraint, where we're going to imagine taking our base LP and adding infinitely many constraints in our minds, one for every real vector of C. You get this constraint, and this constraint is implied by the moment constraints. So just to repeat, here are the key facts. The main key fact is that if like an algorithm imagines the original LP together with these infinitely many constraints, we can actually solve this LP efficiently. And the reason is we're going to actually be able to implement the associated separation oracle. I'll remind you what that means shortly, but that's what's going to happen. Second, remember these moment constraints imply the SDP constraints, but it's a fact that they're not equivalent. Okay, so what we've done here is made a relaxation. We had a program that exactly captured max cut, the original LP with the moment constraint. We relaxed it like the new LP, or the original LP with this SDP constraint, which is now an LP with infinitely many constraints, and we can solve it. So it's not going to exactly capture max cut, but just like we saw in the last lecture where you take an integer program, relax it to an LP, and hope it does like a reasonable job of capturing the problem, that's what's going to happen here. So a key fact is that this new thing that we can solve will give a good relaxation from max cut. Okay, and so for the remainder of the lecture, I want to explain this key point 1. Oops, how we can satisfy this efficiently. Oops, let me get on the right slide here. How we can solve this infinite LP efficiently. And in the next lecture, I'll tell you how you can use it, how you can like round the solution that it gives you to give you this excellent approximation algorithm for maximum cut, which always finds a cut that's within 87.8% of the best optimal cut. Okay, so the last thing I want to talk about is how you can, in polynomial time, solve this like infinite LP that has n squared variables, the YVWs, if n is the number of vertices in the graph, but like infinitely many constraints. And as before, in order to do that, we just need to implement we can do that using the ellipsoid algorithm as long as we can implement a separation oracle. One that can, given some n squared numbers y, it can either check that all infinitely many of these inequalities are satisfied, in which case it's like, done, you've found y's, or it can find a violated inequality, which is to say it can find some real numbers c, which make this inequality fail. I claim, given these y's, there's a polynomial time algorithm that can do that task. And this polynomial time algorithm comes from linear algebra. And this SDP really stands for semidefinite program. And this notion of positive semidefinite matrices is exactly what you need. So a slide or two about linear algebra, some linear algebra that you may or may not have seen before in your life. So a symmetric matrix Y, capital Y, an n by n symmetric matrix, capital Y, of numbers is said to be positive semidefinite, or PSD, if it has this property, that for any real vector C, C transpose times Y times C is non-negative. So that's infinitely many inequalities. And if you just multiply this out in coordinates, C transpose times Y times C is exactly this thing, sum over VW going from 1 to n of CVW. Sorry, this is a typo. This should say CV times CW. Sorry about that. Sum as VW go from 1 to n of CV CW times this matrix entry YVW. So again, this is like infinitely many conditions on a matrix Y for it to be positive semi-definite. But there's going to be some linear algebra to the rescue that will make it less confusing. So matrices Y that have this property are called positive semi-definite, PSD. And luckily, they're actually easy to characterize. Even though there are infinitely many constraints, there's a polynomial time algorithm, polynomial in the number of bits you need to write down Y, such that given a symmetric matrix Y of numbers, it either says, yep, Y is PSD, like Y satisfies all of these inequalities simultaneously, or it finds like a counterexample. It finds an explicit, oh, I still have some typos in this slide, sorry. It finds an explicit vector C such that C transpose YC is not greater than or equal to 0, such that it's less than 0. Okay, so it like sort of tests if a matrix is positive semi-definite, and if it's not positive semi-definite, it sort of finds a counterexample vector C that proves it. And this is based on a linear algebra algorithm that, depending on your linear algebra background, you may have seen before. I'll just tell it to you in a proof sketch. This is not a linear algebra class per se. The algorithm is quite similar to Gaussian elimination, actually. You take this y, and you kind of do Gaussian elimination, but like a symmetric form where, you know, Gaussian elimination, you try to sort of like clear out columns, like make them zeros by taking linear combinations of rows. Like in the symmetric form, like whenever you clear out like the first column of zeros, except for the diagonal entry, you also simultaneously clear out the first row and make it all zeros except for the first diagonal entry. And then you like, you know, pivot again on the second diagonal entry and you clear out this column all zeros and this column all zeros. And you keep doing this. And if you have a symmetric matrix to start, you can sort of symmetrically do Gaussian elimination to sort of form linear combinations of rows that like transform the matrix into a diagonal matrix. I say this if you're kind of half knowledgeable about linear algebra, maybe it'll help. The linear algebra term for this algorithm is Cholesky decomposition. And what you're trying to do eventually is to write y as like this diagonal matrix, sort of times a lower triangular matrix on the left and its transpose, an upper triangular matrix on the right. Okay, so there's, given a symmetric matrix, this Cholesky decomposition algorithm, which is like symmetric Gaussian elimination, actually expresses y as L times D times L transpose, where D is diagonal and L is lower triangular. This is sometimes called like the LDU decomposition. But the point is, y will be PSD if and only if, when you do this, the diagonal entries of D are non-negative. So it's a fact that if you succeed in doing this and all the D entries are non-negative, then the original matrix Y is PSD. And it's also a fact that if you fail, like you come up, as you're doing this, you get some diagonal entry that's negative, you can easily extract from the algorithm a vector C such that C transpose YC is less than 0. Okay, so I'm not going to get into it further than that, but if you do a little linear algebra practice, and maybe it'll be on homework, this proves to be true. And this is also a polynomial time algorithm because it's like Gaussian elimination. It's like an n cubed time algorithm for doing this. There's a question, can we use eigen decomposition instead? Great question. So it's a fact that if you have a symmetric matrix, another linear algebra fact is that if you have a symmetric matrix, it has all real eigenvalues. And another way to define PSD, positive semidefinite, is to ask, or is to say that all these real eigenvalues are non-negative. That turns out to be equivalent. So you might ask, oh great, so given a symmetric y, I'll just compute its eigenvalues, and if they're all non-negative, I say, great, it's PSD. And in fact, if you find an eigenvector with a negative eigenvalue, then that eigenvector will actually be this C that has C transpose YC less than 0. In principle, that works, but actually there's numeric problems because there's not really a polynomial time algorithm for exactly computing eigenvalues, right? These don't even have to be rational eigenvalues. So like you have to get into like, ooh, what if like the eigenvalue is some like negative irrational number that's like super close to 0? Can I like tell whether it's 0 or just like slightly negative, but like maybe has like doubly exponentially many zeros after the decimal point? You get into some weird issues like that. So this is actually, as far as I know, the only truly polynomial time way to test if a matrix is PSD. But intuitively, you can say like, yes, compute the eigenvalues, and if they're all non-negative, it's PSD. Great question. So this can actually be used, this algorithm can be used as the polynomial time separation oracle, right? Because it exactly, given some explicit numbers for y, which are symmetric, it'll either say, good job, ellipsoid algorithm, you found some y's that satisfy all the infinitely many constraints, such that y is PSD. Otherwise, it actually finds you an inequality. This is a linear inequality in entries y, because it's this like sum of CVCW times YVW expression. That's violated. So this really takes advantage of the fact that the ellipsoid algorithm really only needs to run, you know, a polynomial number of variables and the ability to find separating hyperplanes when you think of a point that is not satisfying all the constraints. And so it's a fact of life that even for getting this max cut thing, you can use the ellipsoid algorithm to efficiently solve any quote unquote semi-definite program, where a semi-definite program is like a linear program over variables that are arranged in a matrix, together with the constraint that the variables arranged in a matrix form a PSD matrix. There's a little asterisk here, which I'll talk about, but there's another question here. The question was, for these exponential or infinite-sized LPs with separating oracles, how do we know what value of little r or big R we should give to the ellipsoid algorithm? I guess since the number of bits to describe this k theoretically is infinite because it has infinitely many constraints. Superb question. It exactly gets into this footnote. For these semi-definite programs where you like take an LP plus you put in like these infinitely many constraints, all the stuff that we said about without loss of generality in a linear program, this capital R with poly many bits and this little r with poly many bits exist, and you can throw in the big box constraints, etc. Those are no longer true. This is a very technical point, but they're no longer true when you have a semi-definite program. And so there's two consequences. One, you cannot do this semi-definite programming at all unless you explicitly have big box constraints. You can't just say like, oh, since I have an LP, I can put in big box constraints without loss of generality. In the SDP case, the semi-definite programming case, it's no longer without loss of generality. So you have to explicitly put them in. However, for many applications, that's perfectly fine. Like in this max cut application, we know that all these little y's we're looking for are supposed to be bounded between -1 and 1. So we happily put these in, that y, all the y VWs are between -1 and 1, and then our big R can be 1. It's also true that we cannot, when we have these infinitely many constraints, we cannot have any little r that works. As a consequence, the ellipsoid algorithm can't like keep going until like some finite time and then be like, oops, I know it's either empty or it's not empty. And so that goes into this footnote. You can really not literally solve these SDPs. You can only solve them to additive accuracy epsilon in polylog 1/epsilon time. But, it's usually fine to solve your SDPs up to this numerical accuracy. So this is like mostly a highly technical footnote. So I'll leave it at that. So just real briefly, why, if you succeed, does this imply that the matrix Y is positive semi-definite? Well, let me just put everything out there. It's because if Y is really expressible as LD L transpose, then for any vector C, if you look at C transpose YC, it's C transpose LD L transpose C. If also the diagonal entries are non-negative, then they have square roots. So you can write D as square root D times square root D. It's just the diagonal matrix with the square root of the diagonal entries on the diagonal entries. And so now you can write this. See, now this part here is the transpose of this part here. And so this C transpose YC is equal to this vector times its transpose, which means it's equal to this, it's equal to the squared length of the vector, which is always non-negative. So this proves that if Y really can be written like LDL transpose, where the diagonal entries are non-negative, then it is PSD. And in fact, if you manage to do this, you get this LDL transpose representation, you can write it like this. And now this matrix, root DL transpose, is an upper triangular matrix. This matrix is its transpose, a lower diagonal matrix. And so we see that if you have a symmetric matrix Y, it can be written as Y equals U transpose U for some matrix U. I mean, because these L's and D's exist. And conversely, by this proof that's still written down here, if you ever write Y as some matrix U transpose times U, then this proof starting from here goes through, and you conclude that Y is PSD. So it's another basic linear algebra fact that a symmetric matrix Y is PSD if and only if it can be written as U transpose U for some matrix U. In fact, this matrix U doesn't even have to be upper triangular. It doesn't even have to be square. There always will be a U, which is both upper triangular and square, which satisfies Y equals U transpose U. While conversely, this proof doesn't need U to be upper triangular or square. There should be like, this will be UC transpose, and this will be U transpose C. So that's why this proposition is true. And so it means if you have a symmetric positive definite matrix Y, you can write it as U transpose U. And if you think of the rows of, if you think of the columns of U as vectors, and the transpose has these same vectors as rows. And what it means is that the ijth entry of Y, little y ij, is the dot product of the ith U vector with the jth U vector. So finally, and this is my last slide here, it's also basic linear algebra proposition that whenever you have a positive semi-definite matrix, capital Y, its entries can be expressed as ui.uj, like the ijth entry, there exists some vectors, u1 through un, such that yij equals ui.uj. And actually, this is super similar to the moment condition. Remember, the moment condition that we were trying to capture with PSD-ness was that there are real numbers u1 through un. We call them x1 through xn, but there are real numbers u1 through un, such that yij equals ui times uj. And we replace this moment condition with this relaxed version, this PSD condition. And the PSD condition is equivalent to saying that there are vectors u1 through un, such that ui.uj equals yij. And so next time, what we're going to see is how we can solve the max cut SDP we've cooked up, get these vectors, and then round, quote unquote, round these vectors to integer values to get good max cut solutions. Okay, so that's it. If there are any quick questions, I'll answer them now. Otherwise, I'll stop the recording and then I'll answer non-quick questions. So feel free to hang on after I stop the recording and ask any questions you may have.